chapter 3 is all about minerals. So some minerals would be like silver is an example of a mineral, halite is an example of a mineral, and so is quartz. And you can see that all three of these examples are used in everyday life. So silver gets used in jewelry, halite is a form of salt, and quartz helps make glass. So before we can really get into the details of minerals, we need to look at what matter is. Matter is anything that takes up space, and it can be visible. Oh, let me spell that right for you. Visible or invisible. So an example of invisible matter would be like the air we breathe. The basic unit of matter is an atom. And I think we've talked about this before, but the atom has a nucleus, which is the center of the atom. And then protons and neutrons are found in the nucleus. Protons have a positive charge, P for positive. And neutrons have a neutral charge or no charge. And you can see that we have the protons in red and the neutrons in yellow in this example. And they're clustered together in the center of that atom called the nucleus. And then the electrons are around the outside of the atom, and they orbit around the nucleus. And electrons are negatively charged. Atoms then in turn make up an element. An element is a substance in which all the atoms have the same number of protons. So for example, carbon, all carbon atoms have 6 protons. If you were to add a 7th proton, it's no longer carbon, and it would now be nitrogen. Atoms have the same number of protons and electrons. So that makes, if we have 6 positives, so like carbon has 6 protons, and then since it would have the same number of electrons, and electrons are negative, its overall charge would be 6 plus minus 6 gives it an overall charge of 0. And so we call that neutral. However, atoms can lose or gain electrons. If that happens, we call the particle, it's no longer an atom, it's now called an ion. And so if an atom loses electrons, so that means we have fewer electrons than protons, that means we're going to have an overall positive charge because we have more protons than electrons. If we gain electrons, we're going to have an overall negative charge because we have more electrons or more negative charges than positive charges. Each of these types of anions get a special name. An anion with a positive charge is called a cation. And a way to remember that is the T in cation kind of looks like a plus sign. An anion then is an ion with a negative charge. And anion has that first N to help you remember that it is negative. So atoms can come together and make compounds. So a compound is a substance made of 2 or more elements, and they'll always combine in that same ratio. So for example, water, H2O, is always made up of 2 hydrogens and 1 oxygen atom. And that will always be the case. If you were to add a second oxygen atom, H2O2, this is no longer water. So not water. And it's actually called hydrogen peroxide. So a molecule is the smallest unit of a compound. So here is 1 molecule of water. So now that we kind of have some basics about matter, we can talk about minerals. And minerals are solid. It's key that you remember that they're solid, and they form by what we call natural processes. They can be composed of a single element, or they can be a compound. They are unique and have a specific chemical composition, means that they have a chemical formula like water does. And they have some unique physical properties. So, for example, silver is a single element, so it's made up of one type of atom. Some physical properties is that it's relatively soft, it's shiny, and it's a metal. Whereas salt is now a compound. Its physical properties are white, it has cube-shaped crystals, and then lastly we have a diamond again. And diamonds are usually made up of only one element. That element would be carbon. It's very hard mineral, and it's a translucent crystal, meaning light can somewhat go through it. So when we say that minerals form by natural processes, it means that these processes happen in or on Earth. So a couple examples of natural processes include lava cooling. When lava cools, it will form mineral crystals. Another example would be precipitating out of water. This means that the water evaporates and leaves behind minerals. And so that's what's happened here in this picture. That red bowl used to be full of probably like a salt water or sugar water solution. All the water evaporated, and we're left with either sugar or salt, whatever that white powder would be. And then also high temperatures and pressures cause minerals to grow. And we get these high temperatures and pressures from deep within the earth. So a lot of our minerals form down below earth. And so you may have seen gemstones in jewelry, and some gemstones are actually made in a laboratory, so like cubic zirconium. It is not a mineral because it is not formed by natural processes. So anything to do with in a laboratory is not a natural process. Minerals, another qualification to be a mineral. So the first one is that, it has to be a natural process. Then they also have to be inorganic substances, meaning it is not made by a living substance or living organisms. Organic substances contain carbon, and they would be like our proteins, carbohydrates, and oils. However, inorganic substances, they may contain carbon. They don't have to, though. But they most likely don't. So an exception to this rule here, and this is why I said they may contain carbon, are calcium carbonate shells made by marine animals, so like your clams, snails, crabs, they all have hard shells on them. They are considered inorganic. The third characteristics or requirement of a mineral is to have a definite composition. So this means that no matter whatever makes the mineral be that mineral, it's going to have the same elements and or compounds involved. So some minerals are made of only one kind of element. So like silver, gold, diamonds, graphite, they're all only made up of one kind of element. However, most minerals are chemical compounds, meaning that there's two or more elements. So example, quartz is made of the compound called silicon dioxide, and quartz is a major component of sand, and in turn we use sand to make glass. So like the glass in the windows. Each mineral has its own unique chemical formula. Hematite, another example, has 2 iron atoms. So we say Fe for iron, and we call that Fe2, for every 4 oxygen atoms. So then it's bonded to 4 oxygen atoms. So this is the chemical formula for hematite. The fourth requirement in order to be classified as a mineral is that they have to be solid crystals. So they must be solid. So an example would be ice versus water. Ice is a mineral, whereas water is not a mineral, because water is a liquid, and liquids cannot be solid crystals. Some solids are not crystals, like glass, waxes, and plastics. And so even though I said on the previous slide that we get glass from quartz, glass itself is not a mineral, but we use a mineral to make it. It's not an exception, it's not a mineral, is obsidian. It's a rock, and it's a very glassy rock. And we get this when volcanoes erupt, just right up here. It's very black. And so it might confuse people that it might be a mineral because it was made by natural processes. It's solid. However, it doesn't have the crystal structure. So a crystal is any solid that has its atoms arranged in a very specific pattern. So halite, or a form of salt, has this crystal pattern that we see over here, where we have a purple atom followed by a green, purple, green, purple, green, purple, green, purple, green. And you can see that it alternates, and you can predict which atom would be next in the pattern. So crystal structures are very organized. They usually have a geometric shape to them. So meaning they're either a cube or some other triangle, pyramid. There's some specific shape to it, whereas glasses, waxes, and plastics don't have such a definite shape. Solid crystals sometimes will have 2 different minerals. They'll have the same chemical composition. However, they make different minerals because their arrangement of atoms is different. So for example, both diamonds and graphite are only made from carbon atoms. And so a diamond is carbon atoms that are bonded together in 3 directions, whereas graphite is bonded together in layers. So we have carbon, 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 just bonded together. Whereas in diamonds, it's bonded out in 3 directions, which gives it a much more solid structure. So physical properties of minerals, and we're going to go through these rather quickly because the whole next section is all about these physical properties. So they can have a color. So when you look at them, you can see the color of that mineral. So like sulfur is a mineral with a very distinct yellow color when you just look at it. Streak is the color of a mineral's powder. So in order to determine the streak, you rub the mineral on a porcelain plate. And the crazy thing about the streak is that no matter what color the mineral is, so some minerals come in a bunch of different colors, and even though it's the same mineral, they'll have exactly the same streak. Luster is one of my favorite ways to look at a mineral, is the way that the light reflects off the mineral's surface. So you could have like a metallic luster, which makes it kind of shiny and it reflects light. So like, I don't know, what would have a metallic luster? Like silver or gold has a metallic luster. They could be like non-metallic. And so that is sometimes what we call a dull luster, meaning they don't reflect light. There's minerals out there called like talc, and so they don't reflect light at all. And so you can also have like a translucent luster, like a diamond, where they are kind of shiny, but a lot of light actually moves through the diamond. Another physical property of minerals is the specific gravity. And specific gravity refers to how heavy the mineral is relative to the same amount of water. So this has to deal with a lot of mass to volume ratios. These next two, cleavage and fracture, both deal with how minerals break. Cleavage is a mineral's tendency to break along flat surfaces. So that means you're going to have predictable break patterns. They also, I kind of think of this sometimes as like a stack of Post-it notes. You know exactly where that Post-it note is going to peel off. It's in those nice layers. A fracture refers to the pattern in which a mineral breaks. This is where there's no predictability. As to where the mineral break. These breaks are often jagged and random. And then finally, hardness refers to how hard a mineral is. And you look at hardness, or you can determine hardness by what minerals the mineral in question can scratch and what minerals can scratch it. The hardness is measured on a scale. It's called Mohs hardness scale. And this scale runs from 1 to 10, 1 being the softest and 10 being the hardest. And your hardest mineral would be a diamond. And your softest mineral is what we call talc. Now that we've briefly looked at what minerals or how to identify a mineral and how minerals are classified, we are going to look at different groups of minerals because we need to organize them. Scientists like to organize. And scientists who study minerals are called mineralogists. So remember, ologist means to study. And so a mineralogist studies minerals. They divide the minerals into groups based on their chemical composition. And there are over 4,000 minerals on Earth, and they're divided into 8 groups. So the first group is called the silicate, and silicates contain silicon and oxygen atoms. When they bond together, they form this pyramid shape that we see over here with the silicon atom in the middle. Most of these silicates will also contain other elements like calcium, iron, or magnesium. And this is the largest mineral group with 1,000 known minerals in it. And they also make up 90% of Earth's crust. So silicates, their main components are silicon and oxygen. Silicates then further get divided into 6 smaller groups because the pyramids join together differently. These pyramids can stand alone, they could connect to make rings, they could have single or double chains, they could be in flat sheets, they could join together in 3 dimensions, and so they needed to further organize them. So for example, we have feldspar and quartz. They're the most common types of silicates. Beryl, I believe this one's beryl. They have pyramids that join together in rings. And then biotite mica can break apart into thin, flexible sheets. So you can see how there's like a sheet here, a layer there. There's a layer here. This is the one where I really think of Post-it notes, where it could peel apart. The second group of elements are called native elements, and these are, in my mind, the easy ones because they only contain one type of atom. So these are the ones that you'd find on the periodic table. And there are no other elements. They're very rare, which makes them valuable. Examples here are gold, silver, sulfur, and diamonds, because remember, diamonds are only made up of carbon. Our third group of minerals are the carbonates. Carbonates, as the name suggests, has 1 carbon atom, and they're bonded to 3 oxygen atoms. Again, these can include other elements like calcium, iron, and copper. And they're usually found where seas or salt water used to cover the land. One of the most common carbonates is called calcite. And calcite is an important mineral in limestone and marble. And there are some actually very rare carbonates like azurite and malachite. And they contain copper instead of calcium. And so azurite is right here, malachite is right here. And because of the switch of using copper instead of calcium, we get these vibrant blues and greens to these minerals. Our fourth group of minerals are the halides, and halides are salts. And they form when water has dissolved these salts, and then that water evaporates. And there's more than just table salt. Many of these salts will contain fluorine, chlorine, bromine, and iodine, and some can combine with metals. So fluorite is a cool halide over here, and that contains fluorine and calcium, and it's got a lot of cool colors, and it will glow under ultraviolet light. Oxides are made up of oxygen combined with other elements. Usually 1 or 2 metals will combine with that oxygen. However, it does not contain silicon. So for example, we have hematite and magnetite. They're very, very similar if you look at their chemical compositions. Hematite has 2 iron atoms, where magnetite has 3. And again, our oxygen atoms are off by 1. So magnetite is here, and hematite has this reddish color to them. So apart from the color differences, magnetite is also magnetic, where hematite is not. Phosphates, they have a similar structure to silicates, but the central atom is either going to be phosphorus, vanadium, or arsenic. They're very, very rare, and they have a very complex composition. So for an example would be the mineral turquoise. They contain copper, aluminum, and phosphorus. And turquoise will often get cut and polished into gemstones. Sulfates, are bonded to oxygen atoms, and they can form where salt water evaporates. The group contains a lot of minerals, but only a few of them are common. Gypsum is one of the most common ones. It will contain calcium, sulfate, and water. And gypsum actually gets used in our sheetrock, which makes up walls in many houses. It's found in various forms, and it can grow to be very, very large. So all of this in this image is gypsum, as well as right here. This is, I think, called rose gypsum, because of the color and the shape. Our last group of minerals is the sulfides. They contain sulfur but no oxygen. So this is the difference between the sulfates and the sulfides. Sulfides, no oxygen. So the most common example of a sulfide is called pyrite, which is fool's gold, better known as fool's gold, and it has a greenish gold color to it. So we've looked at what makes up matter, what makes minerals minerals, and the 8 different groups of minerals in this video. In our next video, we'll go into more detail with how to identify minerals.